So, I think that this one's pretty cool. Cosmic filament rotation of galaxies is more proof to my theory that galaxies are similar to atoms and clusters to molecules. So, I've been slowly kind of evolving this concept, and initially I was like, oh well, like atoms are, black holes, whatever. But now I'm not so certain about that. I think that there's different levels to this, and so like in theory, yes, at some level, a black hole could be like an atom, but I think it's more proper to say that like a galaxy is more of like an atom, and then there's different scales to that, and then galaxy clusters that might be what is actually molecules. And some evidence that points towards that is there is this galaxy cluster that was observed in a study, and what they noticed was there was this collective motion or seeming rotation within this within this universal thread. It seemed like all of the galaxies within that thread had a certain angular momentum to them or angular velocity, and it seemed like they were twisting. If this study is true, then the fact that we have a whole cluster of galaxies all rotating seemingly together, this shows them in some sort of bond relation and in a connected more than single galaxy bond, which would be, in my theory, a molecule. And so we know that molecules have like angular moments to them, or whatever is the proper term. We know that molecules have spin, and they spin in different ways, and some directions are more pronounced than others. So when we look at this galaxy chain off in the distance, and we notice that, hey, it's kind of spinning, that to me is very interesting, because then it kind of shows, yes, there is some kind of connection, there is some sort of bond there, and there is this orbital or rotational motion that we expect in molecules here in galaxy clusters. And I don't know, that just makes me really excited. I find it very interesting. And, the fact that they appear to have relational rotation makes sense, and the galaxies having similar spin also makes sense, as they should have similar energy due to their bonds that would align their rotation at a similar frequency. So what I'm saying there is that apparently they also, looking at these galaxies, not only is the collective galaxy cluster rotating seemingly together, right, but it's all of the galaxies seem to have relatively similar rotational energy to them. So not only are they spinning as a molecule, but the individual atoms seem to have similar spins as well. And to me, that seems to make sense, because if they are in a bonded relation, right, the molecule is now a molecule, and so typically the entire molecule is at a relatively the same energy, because it's all bonded together. So if one part of the molecule gets more energy, it gets transferred to other parts of the molecule. So maybe not necessarily all at once, but over time, it evens out. So if you find a molecule that is in this state of stability, this equilibrium, it's going to appear as if they're all rotating at similar speeds, which would result in, similar energy levels, because we know that atoms that have higher energy have higher spin, and this results in changes in their spectroscopy, which we observe as photons. And so the way that we're getting this information of their spin speeds is by photons, because the only way we can see them is through photons, right? Is through looking at radiation and things. And so to me, this is more proof to that point, because now we're literally using almost the same mechanics at the atomic level to observe things and make predictions and get an understanding of what we're looking at for the cosmic level, for galactic scales. And I just find that really fascinating. and very interesting. And I'm curious if like someone could try and apply, the principles of spectroscopy to galactic systems and see what comes out. Do the results like do the results you would expect on the spectroscopy level for, a diatomic molecule play out the same way on the galactic scale? Like if you could find an example of a diatomic molecule, which is potentially, I just did a talk recently about oh no, I didn't do a talk on that yet, but I'm going to, about planetary nebulae within the Milky Way galaxy. They have these, they seem to have it. I think it's just like a star, what's it called? I don't know. It seems to be a pair of stars. I can't think of the term right now. It's something like binary system. That's the word. Right. So it's these planetary nebulae tend to have binary systems from my understanding. And so if we observe these binary systems in these planetary nebulae, maybe that's a diatomic molecule. Maybe we should see what predictions kind of come out there and see if it seems accurate. I don't know. I'm just kind of, putting some stuff out there because, ideally I want someone to try and test these theories and see how well they work. And if they do work, then, more proof. And if they don't work, then okay, either back to the drawing board or, we scrap it. But as of right now, I see a lot of evidence pointing towards my theory being correct here. And so if people could, help that along, that would be great. Anyway, this particular filament is seen as very cold in comparison to others, and so its behavior is less chaotic as a result. So one thing about this filament that they're observing, as I said, it seems to be very stable, as all of the galaxies seem to have similar rotational speeds, so it's in a point of stability, which means that it should have relatively low energy. And the fact that it's like all rotating together also is part of why it has shows stability, because the motion is relatively consistent throughout the whole, in theory, molecule, right? And so you would expect a higher energy, more chaotic system. You would have a whole lot of random rotation happening that wouldn't necessarily, it would almost not be recognizable as a molecule because of the energy in the molecule. However, this one appears to be very cold in comparison to other galactic clusters, and so it's easier to identify this rotational momentum and get the results that they got. And to me, this also points towards more evidence of these being molecules, and because you would expect a more chaotic behavior from a higher energy system. And, as its energy increases, the rotation will appear less oriented, as they will begin to break out of stability and equilibrium, which may result in the breaking of bonds and the formations of new ones. And so what I'm saying there is that when a molecule gets too much energy, it'll break the bonds, right? And then they kind of go off and do their own thing. And I think that is why we don't observe this molecular behavior. One, we're not looking for it, but we don't observe it very commonly because I think a lot of systems still have a lot of energy in them. And because they have a lot of energy in them, they're constantly forming and breaking bonds. Again, we don't observe this because, one, we're not looking for it, and two, because the timescales that these events are happening on is millions of years, and we do not have that much data to, see it, right? If we could have tracked the behavior of galaxies for the past million years, then I think it would be a no-brainer. Hey, I think we know what's going on here, but obviously we don't have that information. We're trying to get an understanding from a snapshot in time. It's very difficult to get a true understanding from such little data. Things are getting better and better, and we're getting more advanced technology, and more things are starting to not make sense with our current models of the universe. not necessarily models of the universe, but our current models for galactic and, cosmic behaviors. Certain things don't play out how we expected them to. Certain things appear when we didn't expect them to. And I think that these are all things that are pointing towards we need a reworking of our model. And the reason why we need to rework our model is because, or rework our model so much is because we just are missing so much data in the grand scheme of things. And so it's hard to get an understanding, but the data is all there. And that's kind of like the exact opposite looking down at the atomic level. We have plenty of time, but no data. So it's like a dichotomy in opposites. And I think that that's pretty cool too, right? So we have all of the data, but no time, all of the time, but no data. And I think that that's funny, but that's why I also think that it's, take the data we have and apply it to the time that we have and see if we can get both predictions to work out, right? And we can get the full understanding by piecing together the missing parts, right? And that's why I think that looking up and looking down together will help us see the full picture. And that's why I've proposed that in the past, and that's why I'm proposing it again, because I really do think that, as above, so below is not just a common wise word for no reason, or wise saying for no reason. Like, I don't think that has significance for no reason. It's because people know it to be true. They see it all over the place within the world that they live in. And so when you look at things in your immediate surroundings and notice this behavior, you start to wonder, well, if it's there, why isn't it, and if it's there and it's there and it's over there and it's everywhere that I look, maybe it's also happening in things that I can't see as well. And that's why I think that it's a good thing to kind of look into. There's this certain esoteric and mystic wisdom that I don't think is just wisdom and good advice for no reason. I think that this has backing to it because it's been found to have truth to it. And this hasn't been scientifically proven, and so it's not accepted in our current society. But just because science hasn't proved it yet does not mean it's not true. It just means that we need more data. And I think we can get it. We just have to, do that. So anyway, peace out.